Okay, an IOC question, right? I even give you a hint on this exam. I said to those people, I said, remember to check your endpoints. See, that was nice. I usually don't do that. I must really like that class.
You really like our class.
So we're doing
Because I didn't do it on
7?
13. Notice on 13 it
Yeah,
just said, what's the radius, what's the interval? I didn't say, check your endpoints.
You love this class, don't you?
Yeah. I love all the classes, but I don't, that's unusual.
Especially this class.
Okay, so,
Every Friday.
let's see, n equals 0 to, and I've got an n plus 5 here, and I've got a 17 to the n here, and I've got an x minus 4 to the n, and it's an ROC IOC question. Okay, so remember the big theorem on power series. Three things are going to happen with a power series. What are they? Give me the three
Ratio.
things that will.
Ratio or root, and then.
No, not how to do it.
Oh,
Ultimately, there's only three possibilities for the answer. What are the three possibilities?
absolute convergence.
Absolute convergence where?
In the interval.
Okay, thered be a positive R, so that's one of the possibilities, is that there exists an R is greater than 0, and you would have, when, say here, for A is 4, so when the absolute value of x minus A is less than R, you get absolute convergence. And when the absolute value of x minus 4 is greater than R, you get divergence. Okay? And then when it's equal to 4, you gotta check. Okay, so that's one possibility. What's the second possibility?
R equals A.
R equals,
It converges at R equals
not R,
A. Or X equals
no, R would be 0, and it only
A.
converges
right,
at, it only converges at A and nothing else. So it might only converge at 4 in this problem. And then R is 0. And then what's the last possibility?
Converge everywhere.
Absolutely converge everywhere. Yeah? So you would get absolute convergence everywhere, in which case R would be infinity. So it's going to be one of these three cases. I guess since it's a final exam and I'm trying to test you with endpoints, it's probably going to be case 1, but you never know. But yeah, and in this case probably is. So let's run a ratio test with the absolute value as guaranteed by the theorem. Let's force the outcome to be less than 1 to make the ratio test successful in order to get a condition on x, because x is our variable. So what we're going to do is we're going to run a ratio test. We're going to run a ratio test with the absolute value, and we're going to force it to be less than 1 to get a condition on x. Okay, so we're going to take a limit as n goes to infinity of the absolute value of n plus 6, x minus 4 to the n plus 1.
He's adding 1 to it. You have to add
Adding 1. So it's the n plus first term, right? It's the n plus 1. So this is going to be a 17 to the n plus 1. And now I'm going to divide by that, so I'm going to multiply by the reciprocal. And so I have an n plus 5. x minus 4 to the n, and I force this to be less than 1. Okay? And so where is my cancellation?
X
X
minus
minus
4
4
to the
and-
n is canceled.
All of this is gone,
And
that's gone,
N plus 1.
that's it, yeah?
Mhm.
So I've got a absolute value of x minus 4 over 17 times the limit as n goes to infinity of n plus 6 over n plus 5 less than 1. I've got an if and only if. And what is this limit?
1.
1. So it's if and only if the absolute value of x minus 4 is less than 17. That's the condition I'm getting on x. Which means that R is,
R is 4.
no,
17.
A is 4. What's R?
17.
17. So your ROC is 17, your A is 4, you're here at 4, and you're out to 21, and you've got absolute convergence in there. And then on this side, you're at negative 13, and you've got absolute convergence throughout there, right? And then you've got divergence out here, and divergence out here. And you just gotta check this, and you gotta check, so you negative 17 and 21. You gotta check. So, if it's 21, what happens? It does what? If I plug in a 21 for x, what do I get? What happens here?
The 17th, yeah.
17 over 17 to the n's cancel. What about a series n plus 5? Converge or diverge? Diverge. Oh my goodness. Oh my goodness. Oh my goodness. Does n plus 5 go to 0 as
No.
n gets big?
No, it's big.
So it fails the test for divergence, which means, or it tells you that it diverges, right? Didn't go to 0, right? It failed going to 0, so by the divergence test you can determine that it.
Do you want us to show that? Or is that where you want us to?
Yeah, I mean, I would say, look, I mean,
I'm just gonna look.
you're asking about series n plus 5, well, the limit as n goes to infinity of n plus 5 is certainly not 0, so diverge. It's your nth term test or your divergent, what I call your divergence test. So, and what if it's alternating n plus 5? What about that? So what if you put in negative 13, you get an alternating n plus 5? Is that going to go to 0? Of course not. Right? So, fails here, fails here. So, what's your interval of, what's your IOC?
Open interval.
Open. Negative 13 to 21. Open. Done. Okay? Guaranteed to get a problem like this.
Is 17.
Oh. What's the interval of convergence? It's guaranteed. So, and I say, what's the interval of convergence? What's the radius of convergence? Guaranteed question.
17 is the.
17 is the radius of convergence. 4 is the center. Okay.
And you plugged in the n plus 5 into the original, and that's why you knew that or you plugged in 17 into the original, so that's how you knew that was
And I got cancellation.
Right.
Okay,
Improper integral.
yeah, okay, I threw one in. So I could have done a series, or I just, but here I just wanted you to actually do the evaluation.
That he got
Yeah.
10, the reason you could
Like,
say that
is that
n plus 5 diverged is because
So-
you plugged in 17 into the original, and then the n and the 17 canceled, right? So that's why you got n plus 5. No, sorry, it wasn't 17 minus 4,
You
it
have to add
was,
4, I think.
it was 21 minus 4.
That's 21 and 13, negative 13.
Yeah, so you plugged in the 21 minus 4, which canceled with the.
So I could have asked you about the series, and then you could do the integral, in which case you'd be doing the problem that I asked them to actually do on this test. But if I gave them this, they don't have to do an integral test, right? They could have done a comparison test, a limit comparison test with like 1 over x cubed or something like that. Would have worked. Easy limit comparison test. So that's why I asked specifically, okay, actually do the integral. So you're going to have improper integrals either specifically being asked about them or through an integral test. So you always, you replace with t and you take a limit as t gets big. Now you have to integrate this. How do you integrate that? By parts. So you do parts box, ln x, g prime, x to the minus 7, g, f prime, 1 over x. What's the antiderivative of x to the minus 7? X to the minus, I'm hearing 6 and 8, which one is it? 6. X to the minus 6 over minus 6. So, we've got ln x over minus 6 x to the 6th minus a minus, so plus the integral of, it's going to be 1/6, and then this is going to be x to the minus 7. But you already know that, it's this. So you're going to have ln x over minus 6 x to the 6th minus 1 over 36 x to the 6th. So there, I guess you could make this get a common denominator, yeah. So why don't we make this a, let's put a plus here, put a minus here, put a 6 here, and put a minus 36 there. So then we'll put a 6 ln x plus 1, or I guess we put the minus sign there, put the 36 x to the 6th, okay? There's antiderivative. Okay. Now, we're going to be evaluating from 2 to t, and you have to take this limit. T gets big. So, what's going to happen? What's going to happen when you plug in t? What's the ln t versus the t to the 6th? This is going to win. This is going to go to 0. Now you know that intuitively, but I guess you probably should do a L'Hopital's rule or give me something to convince me that you understand that the limit as t goes to infinity of minus 6 ln t plus 1 over 36 t to the 6th. That piece is 0. Do a L'Hopital's rule, easy. That's going to be 1 over t. That's going to be so you're going to have like a 6, minus 6 over t. Here you're going to have a what? A 2 what's that, 216t to the 5th. And this, you can make this a t to the 6th, and then it goes to 0. So do something, do some L'Hopital rule, do something. And then you're gonna be subtracting what it is at 2, so you're gonna be subtracting the minus, so you're gonna be adding. It's just gonna, the answer is gonna be 6 ln 2 plus 1 over 36. 2 to the 6th is what, 64? Whatever that is. Okay? Okay.
So it converges after that.
Yeah. What about, oh, the next one, arctan, you could do this one really, this is really easy. So, what do I have here? I have a, I have an arctan over a, over 1 plus n squared, and now I raised it to 26th power. Who cares, really? Because if you did an integral test with that, your antiderivative would be arctangent x to the 27 over 27. Because you have the derivative of the inner. So, since arctan, when t gets big, arctan t goes to pi over 2, who cares? Raise pi over 2 to the 27th power, it's still convergent. It's still a real number. So, this is going to converge by an integral test. Right?
Can we do like a direct comparison?
You could do a comparison, you could do a limit comparison. So you could do a limit comparison with, this, because this is a known convergent. So if you ran a limit comparison test with arctan n to the 26, 1 plus n squared divided by 1 over n squared, and get the n squared up here. And then this part is going to go to 1, this is going to go to pi over 2 to the 26th. Well, that's a positive constant, so again, case 1 of limit comparison test, you could have done a straight comparison test with, I guess, pi over 2 to the 26th over 1 plus n squared is greater than
Wait, why is it pi over 2
arctan
again? Because arctan.
n to the 26th over 1 plus n squared.
It's just saying that this is arctangent.
And I guess you could argue this is less than pi over 2 to the 26th over n squared.
So arctan.
And you know that 1 over n squared converges,
Oh, right,
so
'cause if you
multiplying by a
look at
constant makes it converge. You could have done a straight comparison. You could have done a CT. I would have accepted a CT. I would accept a CT, an LCT, or an integral test on this. So an LCT is CT or an IT. As long as you do them correct. Okay? Okay, integral test. I'm hinting an integral test.
Yeah, greater than 1. This one doesn't have anything.
Okay, I'm suggesting an integral test. Okay, so, by the way, take my suggestions probably. I give suggestions, I'm trying to help you out. So, let's do an integral test, so.
Positive.
This is X. Yes. Okay, so let's do an integral test here. What do you want to sub on?
ln x.
Yeah, so first of all, make this a limit as t goes to infinity, integral 3 to t, 1 over ln x squared times 1 over x dx. So do a u sub, u is ln x, du is 1 over x dx. This is going to become 1 over u squared, or u to the minus 2 du. So what is this?
U to negative 3 over negative 3.
Negative 1
Oh,
over.
so U to negative 1 over.
U to the minus 1 over minus 1, or ln x to the minus 1 over minus 1. So that's going to be 1 over minus ln x. And then we're evaluating from 3 to t. But when you take the limit, what's going to happen?
It goes to 0.
Yeah, this, the 1 over ln t, so the limit, as t gets big, of 1 over minus ln t, this piece is going to go to 0. Then you're subtracting the minus, so you're going to be adding 1 over ln 3. So there's your answer. All right, it converges here. So since this converged, and then this converged.
Do we have to do this, the 3 rules on like convergence?
Mhm.
Show it's positive, decreasing.
Yeah, but with this one, the justification, yeah, so it's positive, well, that's easy. It's continuous because it's, n is continuous, ln n is continuous, ln squared is continuous, the product of two continuous functions is continuous, and then 1 divided by what is continuous, so the quotient of two continuous functions is continuous, and so the whole thing is continuous. And then decreasing is easy because you don't have to do a first derivative test here.
It converges to
Because
1 over ln 3.
Yeah, but.
It's kind of clear when
It doesn't
you
matter, you just have to know that it converges.
make that denominator
It's like
larger, it
1
makes
over-
it smaller. So you can make an easy argument that
Not even plug
way.
in.
Or you could,
So we
Oh,
can
Or
so
you
it
could
it
do
be
a-
anything, we're just.
yeah, or you
testing
could
the
do a
algebra.
first derivative test and show that
That's
So
the
instead of
first derivative test was
you just said
negative, I
minus
accept
C.
a negative first derivative test. So
Save more time.
when
Really?
it's
So I
prime
could've said
less
like
than
this minus
0,
C, this whole
then
thing.
f is
Okay, 'cause this
decreasing.
is
You
just
could,
constant.
There's gonna be
you
some
could do a
constant.
1b.
Okay.
But you
It's
don't
only
have to,
for
I think it's pretty obvious, but
You're doing
yeah,
action
good,
roll, then
good to
also.
state
Okay.
the positive,
It's
decreasing,
because it said- it didn't
continuous
say about-
during an integral test,
Yeah, you're doing a
okay?
test.
Right.
So, I think that last question we did, the code, that's the one you did on the quiz, right? The integral of cosine 7x over x, I think you did that, I think that was the quiz question. From the group quiz, I think we did that, so we already did that one. And then oh, that's the 13. Oh, this is the sine x over, so back on 12, the integral of sine x, sine 7x over 8x, it's the same thing, right? It's the same type of thing, so.
Don't pause.
Okay, so you're gonna substitute a series for sine 7x. So remember that sine x is a sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Methodology, you can just substitute the 7x in. So the sine 7x is just a sum from n equals 0 to infinity, -1 to the n, 7 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. So just take this and throw it up there. Alright? Now when you divide by x, you just drop that power to 2n. So in other words, the x to the 2n plus 1 divided by the x is just going to drop this power. So what you're doing is you're integrating series of -1. You can take the 8 out, the 1/8 outside, and then you're going to have a 7 to the 2n plus 1, and then you're going to have an x to the 2n. And then you're going to have the 2n plus 1 factorial, and then dx. So you're integrating here. Yeah? And you know how to integrate that. You're allowed to do it term by term. You have a nice theorem that tells you you can do that. So you're going to get what? What are you going to get? You're going to get series what? You tell me. What's the antiderivative of that stuff in there? You're integrating dx. What happens to all this stuff?
You can push it to the side.
Well, it just stays there, right? So you're going to get series -1 to the n, 7 to the 2n plus 1, divided by 2n plus 1, factorial. What's the antiderivative of x to the 2n?
2x to the 2n plus 1 over 2n plus 1.
Yeah, so you're going to have an x to the 2n plus 1 over another 2n plus 1. That is your answer. I won't take off a point. Okay? So,
How did you plug that in though? Oh, you plugged it. Where did the sign go when you plugged that in? Like I don't.
You know why?
It's the exact same thing. So you said you
sine
plugged
7x
it in.
is this whole thing, so I took this whole thing and I threw it here.
And then you just.
And when I divide it by x, when I take, see if you take this whole thing and you divide by x, the only thing that is affected is that goes. So that's why I got that, x to the 2n. Because x to the 2n plus 1 divided by x is x to the 2n. And then you anti-differentiate that term by term.
Okay. Because it's like so those are just.
Okay? I think we're a wrap. I better get down to the last 20 minutes of the excitement down to the Aloha Tower.
I heard it was intense.
It's great, and it's hate to miss it, but I'm devoted to my students. That's why I'm here. I'm here for my students doing a review session. And I feel a great duty to attend that meeting too, but I'm here for my students. And I'm going to that meeting. And I'm racing down to Aloha Tower to attend the end of the meeting.